Testing, testing. Welcome, everyone. We'll get started in just a couple of minutes. Hang out temporarily while I get a couple of windows situated. All right. The word is out, posted to social medias. All right, I've been doing a couple of new things today with today's production. Got an iPad set up so that I can draw out some math, and hopefully we can talk about some concepts spatially in that format in a way that'll be slightly better and faster than having to code everything. Today, I really want to talk about covariance and correlation. But in order to really understand those two concepts really well, we're just going to double check our understanding of variance and standard deviation. And I think if we really truly understand variance and standard deviation thoroughly, then it will be a lot easier to wrap our head around covariance and correlation. So when I go to switch to the iPad here and do some diagramming, things like that, if you notice any technical difficulties, if you can't see my screen, if you can't hear me, etc., please let me know. But before we dive in here, I am going to share in the chat a link to the starter notebook. And a link to the live lecture notebook that I will be coding in. For your reference. They also will be linked to in the description of the YouTube live stream archive after the stream's over, and will be added to the temsi.com/machine-learning-workshop page where you can always find an archive of all of our past live streams. Cool. Before we dive in, there's like one slight preamble I want to say. I've made some notes here at the top of this file. Let me make the font a little bit bigger. Hopefully not too big. And we've already talked about a lot of descriptive statistics: mean, median, mode, range, interquartile range. Talked briefly about variance and standard deviation, skewness and kurtosis, right? And these kind of get categorized in traditional statistics courses about being called measures of center, measures of spread or dispersion, and then measures of shape. And this regression and correlation section is what we're building up to, where we're headed next, right? Today, I really want to make sure we have a really simple, really solid understanding of covariance and correlation. And then that will really enable us to hopefully easily get into actual linear regression modeling. We'll do both what's called simple linear regression and multiple linear regression, or simple linear regression is sometimes called bivariate linear regression. We just have one x variable and one y variable, right? And really be able to break it down and understand linear regression. But in the context of predictive modeling, where our end-all be-all goal is to make the best predictions we possibly can, we're probably going to turn to some kind of regularized form of linear regression. Regularization just means the weights of our model, they may get a little bit extreme, and we're going to implement a strategy for keeping those weights from getting too extreme so our model doesn't overfit to noise in the data, right? And we'll talk about these kinds of regularization methods with linear regression that all get different names: ridge regression, lasso regression, elastic net regression, and some other ones as well, right? But that's where we're headed. And I'm really trying to lay a solid foundation so that once we get to linear regression, once we get to regularization, we'll have a really solid foundation for getting into those topics, and they'll just make a lot of sense to us. Now, there's kind of a divider here in the notebook, and then below this, there's some probability and inferential statistics topics that are also important that you be aware of, just as a general reminder about, you know, if you wanted a checklist of things that you should learn about statistics that are going to help in data science, I would add these on as well, but we're not going to touch on these as directly throughout our discussion of linear regression. We're going to cover these topics really well, these ones a little bit, right? Now, in the world of statistics, there's kind of two camps, two purposes, two approaches, and I sometimes refer to this as the inferential statistics approach versus the predictive statistics approach, right? And inferential statistics is all about having a population and sampling from that population and exploring to what degree does that population speak to to what degree does that sample speak to the population, right? And if we have some kind of a metric about the population, we call that a population parameter. And those metrics we have about the sample, we call those sample statistics, right? Part of where the field of statistics gets its name. And then we can do things like hypothesis testing and build confidence intervals and all those kinds of things around random samples. And verifying the randomness of samples and sampling correctly is a whole science in and of itself. And you could take an entire university course just on setting up proper experiments and sampling correctly and all sorts of different sampling methods. In data science, our data set we kind of treat it like a sample out of the box. We don't always verify that it's truly a random sample, but we're going to assume that if we train on this data, our model's going to learn how to generalize to quote unquote unseen data. You can think about that as like generalizing to the population, right? And so there are some inherent similarities in machine learning to inferential statistics, but linear regression in particular, inferential linear regression, is all about proving some causal effect of an x variable on a y variable. It's all about the interrelatedness between variables, whereas we only care about the interrelatedness of variables to the degree that it helps us make better predictions, right? In predictive statistics, the goal is generalizability and quality predictions, and everything else is secondary to that. And so as we get into linear regression, we might talk about it from a little bit of a different lens than you may have experienced if you have studied introductory statistics at university or done, for example, in my undergrad in economics, we did econometrics, which was basically using linear regressions to prove, quote unquote, prove a causal relationship between some x variable and a y variable. And that's the bulk of academic research, is using linear regressions to show causal effects and trying to get a p-value and do hypothesis testing in a way that shows that you found some statistically significant finding in your research, right? And that's all very academia focused and not what I'm interested in. I want to make awesome predictions, and I want to be able to tell the future with my awesome predictions. I'm not as interested in like publishing in a journal, or else I would be, you know, pursuing academia right now, but I'm not. I'm here teaching you on the internet. But so that's just a slight soapbox, a soapbox I may get on again in the future and talk a little bit more about. But just trying, as I try and constantly and consistently give you a roadmap and help you understand where we're headed, where we're currently at, what we're going to be talking about today, I wanted to address some of those things. Are there any questions about that? Okay, and if you do have a question, keep typing. I'll see it in the chat. Sometimes there's a little bit of a delay. So if I get talking again, don't think that means you should not answer, ask your question. All right, so measures of standard, we've already talked about these. Mean, median, mode, range, the max minus the min value of our data set, and the IQR, the interquartile range, which is the distance between, or the difference between the 75th percentile and the 25th percentile. We saw that in the box plots we made last week. We also saw the mean and the min and the max in the box plots. Box plots are really great for showing these different descriptive statistics visually, helping us get a visual comparison. And I want to talk very briefly, slightly more in depth about the median and the mean, just real fast today. And part of that's because on temsy.com, I have written a variety of code challenges that I would like to challenge you to try and solve. And a lot of them go hand in hand with the topics we've been talking about over the past 2 to 3 weeks, right? Can you calculate the mean of a list? Can you calculate the median of a list, the variance of a list, standard deviation of a list, sample covariance of a list of values, the correlation? We're going to be able to do all those things by the end of day today. And so come to the code challenges site, see if you can try and solve these on your own. Once you click into a code challenge, you'll write your code here trying to, well, you won't be able to see this. This is the test that tests your code, evaluates if it's right or wrong. You won't be able to see that. So you're kind of getting a peek behind the curtain here. But you'll run your code. Running your code gets it in the notebook's memory. And then once you run your code, you have to submit. So every time you have to run your code and then submit. It's kind of a 2-step process anytime you want your code to be evaluated. And if you hover over a code cell, you can see potential solution to this code challenge here. If you get stuck and you want to kind of peek at a possible solution, just dive in, see if you can give those a shot. And what I would really love is if you have any feedback about the user experience here, how to make things better, some things that are confusing, or if you find any bugs, or if the instructions are unclear, any of those things, I really want to keep on improving these code challenges, making them better and better, and adding more as I'll be doing as consistently as I can. This is going to become hopefully a really awesome resource for really testing your mastery of these different concepts. So just wanted to bring that up, and I've linked to different code challenges throughout today's documents. Right, so this is the median of a list code challenge, and you'll see those as we scroll through. I'm not going to point them out, but if you want to click on them and do them, I would highly encourage it. All right, so the median. It's the middle value of a data set when the points are arranged in ascending order, right? Oh, and by the way, my runtime is restarted, so I've got a few useful Python modules up here. I'm going to load those and then come back down to the median you were talking about, right? So if I make a column of a data set, like a data frame, where it's just literally just a list of numbers, right? Well, right now they're not in order, right? So if I look at the middle number right now, it's 6. 6 is not the median. I first need to sort them. And once they're sorted, it becomes really easy to see the middle number, 3. We have got 5 numbers here, so the middle number is this one right here. That's the median of this random variable we're calling x. It's really a creative name, right? Well, I want you to see that. Let's copy this. That the median is really resistant to outliers, right? If I change this from 6 to 6,000, does it really change the median? No, that middle number stays the same. Right? And we saw that the median was resistant to outliers when we looked at skewed distributions. We saw that the mean got pulled further further off from the center of the distribution than the median did. And this is us seeing that resistance to outliers that is inherent in the median. Okay, but one thing that I want to talk about that you maybe don't think about a ton, and that you might want to know if you want to try one of those code challenges, is that the median does something slightly different if we have an odd number of observations, right? So let me add one number here at the end. So instead of having 5 observations, 5 numbers, we have 6 now. Okay, now we're going to do the same thing. We'll sort them. Okay, but if we have an even number, we want to look at the middle 2 numbers and average them. Okay, and this is kind of a tricky thing. We need, right, let's get our sample size, or the number of observations. Here we'll call that n, as we typically do in statistics, right? And then I want these 2 values, but the position of those values could change based on the number of items I have in the list, right? So I need some way that I can compute the index positions of these 2 values inside the list, no matter the length of the list. Okay? There's actually a lot of ways to do this. Here's how I'm going to do it. We're going to take the sample size minus 1, the number of observations minus 1, and then we're going to do what we call integer division. We're going to divide by 2, and if there's any decimal portion, we're going to round that decimal portion down to the nearest whole number. And that's going to give us the left index. And then the right index, so that's going to give us 0, 1, 2 here. Right? That's the position of the number 3. The right index is just going to be the left index plus 1, because we're just going to look at the one next to it. Okay? And so if I print these 2 out, we have index positions 2 and 3. So 0, 1, 2, and 3. So these are not the values in the list themselves, they are the index positions. I've probably said that a million times. And then the median is, you grab the item that's at the left index, add it to the item that is at the right index, right? And if we are averaging 2 numbers, all that means is that we add them up and then we divide by 2, because there's 2 numbers, right? Add up the number of numbers that we have, divide by the number of numbers that we have. So the median here, if I print it out correctly, is 4, right? It's the average of 3 and 5. Okay. So you may not have thought about this very often. In like traditional statistics classes, they usually just give you an odd number of values. So there's always one exact middle number that is the median. But if you have an even number of values, then you have to follow this process and average those 2 middle values, which is a little bit tricky. All right, so that will give you a little bit of a head start on the code challenge. There's also one other wrinkle I haven't showed you about, like, how do we detect if a list has an even or an odd number of values, right? Well, whoops, I don't want a text cell, I want a code cell. The length of x is 6, and if I use the modulus operator, so I divide that by 2 and I see if there's any remainder after I've divided by 2. That's what the modulus operator gives me, right? So if this is an even number, then there's no remainder. 2 is a divisor of this. It divides evenly into the number. So if whatever the length of your variable is, the number of the observations, mod 2 is 0, then it's even. Okay? If we have an odd number here, then mod 2 will be 1. So that's the way you can differentiate between lists of odd or even quantities of numbers using the modulus operator, right? So it's not very often we run across instances where we have use for both integer division operator in Python and the modulus operator. Those are 2 a little bit more rarely used operators, but which is part of why I wanted to show you this today. It's not super often we get a chance to like see those in action and really benefit from them. So that's a little bit of a head start on the code challenge. Okay. Now we're going to move on. We're going to talk about the mean, or the average, right? And we're going to look at this crazy equation over here. I'm going to make this way bigger than I should because I just want to look at this equation and make sure it's big enough that you can see it, right? In statistics, when we talk about the sample mean, we denote that as x bar, x with a line over the top of it. So this just means the sample mean, if you see x bar. And then this expression on the right, x sub I, the sub I means that we're going to look at each individual value in our list, one by one, and we're going to do whatever this operation on the right side says. In this case, it says just look at the number, tell us what the number is. And then we're going to, after we've done this operation over here, we'll sum up all of the values after that operation's done. This is the summation symbol, and then divide by the number of values. So at the end of the day, we're really just summing and dividing by the number of values, right? But I bring this up because the mean, or the sample mean, is going to be used in some of the other things we talk about today. It's going to be used in the variance, and then things are going to cascade down from there, right? So what is x sub I, right? If I've got my list here, I'm just going to copy and paste this from my notes, right? You can think of this summation symbol as being a for loop, right? For x sub I, I'll write it like that, in whatever our list of x values is. All right, we're gonna print out each of these by one. We're looking or looping or stepping through this list, through this sequence of values, what we call element-wise. It means element by element, item by item, right? And in this case, I'm not doing anything with them. I'm just printing them out, okay? But usually, as I'm looping with this summation thing, I don't want to just look at them. I also want to add them up. I want to get a running total of all these values, right? So I might do something like, we'll make a variable here called total and just initialize that to 0. And then instead of printing inside of our for loop here, we'll add our whatever current number we're looking at to that running total. And this is going to have the function of summing everything up. Okay. So 17 is 1 plus 5 plus 3 plus 2 plus 6. So that is a summation, like a very verbose for loop summation. But then if I want the mean, afterwards I divide by the number of observations, or the length of x. So the mean of this list is 3.4. That is the average value. Okay? But Python usually has a lot of ways that we can avoid writing for loops if we want. So Python actually has a built-in sum formula. We'll get exactly the same thing with way cleaner code, right? This summation formula is the same thing as all this. But it verifies that we got the right value, right? And we can even use other libraries if we want. Turn it into a NumPy array, which has a built-in mean function, etc. Okay. So I want to turn to our iPad now, and I want to visualize something about the mean for you, and try and help you think about the mean in a way that you've maybe never thought about it before. Maybe you have, maybe you haven't. But I hope that, like, even if you've studied statistics, that we can do some cool things today that will just deepen your intuition of these measures a little bit more. Okay, so I'm going to try and switch screens. If you end up not being able to hear me when I switch screens, I switch to the iPad or see my iPad display, please let me know in the chat. Here we go. Here goes nothing. Okay, can you hear me now? Thank you for letting me know, Caesar. Is that any better? Okay, perfect. Thank you for letting me know. Okay, so we were talking about, I was going to say that I want to show you using my a really mediocre drawing here, hopefully some things you've never really thought about the mean, and it'll make it so that the way you think about averages will be really intuitive, because we're going to see that some of the other statistics we talk about today are really just averages, but of certain things, right? So in this scenario that I've drawn for you here, we have 4 cups of water, and we're going to say that the levels of water in each of these 4 cups is at different heights, right? What could we do to average the heights of the water in these cups? In other words, make it so that each cup has exactly the same amount of water in it. Okay? What could we do? Sorry about my really, really great drawing. Well, maybe we have a pitcher of water. Wow, is that a really good pitcher of water? And we pour the water from each of these into the pitcher, and so we put them all together. So then each of the cups is empty, right? Okay, so now we've got a bunch of water in our pitcher. Then what do we do in the pitcher? We're going to pour very carefully amounts back into each of the 4 cups until they're at the same heights. And if we mess up, we can pour some off, pour it back in. But like, this is essentially what we've done with the mean, right? We summed everything up, right? And then we redivided back into the containers we started with, into the number of items we started with. So you could think about the levels in each of these cups as being our the values in our list, right? Maybe this is 1, 2, 4, 3 when we started. Those were the heights of the water lines. We summed them all together, and then we redistributed in however many observations we started with. So the number of cups here, that is n, that's our sample size, or in Python terms, that's the length of x, right? In this real world example, I hope that it's just a slightly different lens from which you've maybe never thought about averaging things out before, or creating balance throughout this division within the data set. Okay, so this is gonna, I hope this is clicked to some degree. I hope this is like a way you've maybe never thought about a mean, or what we're going to talk about, a measure of center of some statistics, but this is going to come back up in a minute. Okay, do you have any questions about this? About this example before I erase it? Okay, maybe a little bit silly, but it will be relevant. We'll see in a sec. Okay, so a reminder, x bar is equal to, oh, can you see that? I got to write it a little bit lower. X bar is equal to, well, the sum of x sub I divided by n. Let's clean that up. Okay, that is the mean. Okay, now I want to turn our attention to, oh boy, I don't have the exact same, that's the mean. Okay, now I want to talk about variance. Okay, what the heck is variance, right? So here's another thought experiment. Less of a physical world thought experiment, but imagine we have a data point out in the lonely world, right? Variance is a measure of spread, or a measure of what we call dispersion It's a measure of how spread out our data points are. If I just have one single point, how spread out is this one single point? Well, geometry tells us that a single point in geometry has no width. It's an infinitely small, tiny location, right? So the variance of a single point is 0, right? This has no variance. It's not spread out. It has no dispersion. It has no width, right? Okay. So if you only have one data point, your variance is 0. What if I had 2 data points? If I wanted to come up with a metric that could summarize how spread out these 2 data points are, what could I do? Well, I could maybe get out a ruler, or maybe make a number line of some kind and measure them along that number line. Maybe this is 0, 1, 2, 3, 4, right? And I could look at the distance between the two. Okay. If I wanted to calculate the distance between these 2 points, what should I do? I want some measure of dispersion, of spread outedness. What math calculation could I do to calculate that, given these 2 points? Well, I could subtract them, right? So I could take 1 point's position, subtract that from the other one. So I could do 4 minus 1, the top point minus the lower point, and that would be 3. Or I could do it the other way around. I'm the one making up the metric here. I get to choose. I could do 1 minus 4. That would give me negative 3. Okay. So typically we would like to take the bigger number minus the smaller, but when you think about subtraction, okay, in statistics we call the distance between 2 things, we call it the deviation. Okay, so it's similar to the difference, which is what subtraction finds. Subtraction finds the difference, right? But at the end of the day, I want a distance between these 2 points. These are all kind of synonyms for each other, so I'm writing them in quotation marks, right? But the word we're going to keep on using today, we're going to keep on calling this deviation. Okay, it's a very important word. Okay, we want deviations to always have positive units, right? So we would like to calculate the deviation using this metric, or we could maybe take the absolute value, right? After we do whatever this calculation is, we could say, oh, we want the absolute value of 4 minus 1. Wow, and that makes it really hard to tell what's going on. That looks like an 11, right? Let's make that a little more extreme. Or the absolute value of 1 minus 4. Okay, so the absolute value would make this a plus sign. They would both be positive. And that's good because there's no such thing as a negative distance. There's no such thing as a negative deviation. It always has to be measured in a positive number. Okay. Another thing I could do is instead of taking the absolute value, I could square this deviation. Okay. And the square of any negative number always ends up being positive. So in both of these instances, I would end up with 9. Right. Negative 3 squared is 9, and 3 squared is also 9, right? So this is also a way that I can consistently generate a positive measure of deviation, okay, by comparing one against the other. Either of those two methods should work out for me, okay? And when we do this, we call this the squared deviation. And squared deviations are everywhere in statistics. Everywhere. Anytime I want to say, how different are these two things? Probably some kind of squared deviation is getting used. And that's really what I'm doing here. How spread out are these points? Is asking the same question as, how different are these points? How different are their values? Right? So, squared deviations are where it's at. Okay. Let me clean up a little bit here. All right, so we understood the concept of a squared deviation. We'll revisit it. It's not going away. Okay. What if I had a third data point? Or a fourth data point? Now how do I measure deviation? Right? I don't have an easy pair of values. Like, what should I subtract from what? Right? What's going to be my base? Should I measure deviation from 4 and get all those distances? Or should I get the deviation from maybe from here? Right? There's no way to pick who's going to be the anchor, who's going to be the rock, what are we deviating from, right? If we have more than 2 points, then it becomes a lot trickier. So here's what we do. We make a fake imaginary point at the center of this distribution. Well, that's called X bar. X bar is the sample mean, and X bar is always at the center of the distribution. And instead of measuring the distance between some actual data point, we measure the deviation from the sample mean. Okay? So in this instance, right, if I were to take these numbers and turn it into a data set, right, if I were to put it in a data frame, it might look something like this. So here's a column of my data frame. My variable is called X. And what are my values? I've got 0, 1, 3, and 4. That's in my CSV file, right? This is my tabular data right here. Okay. And then if I want to calculate the deviation, I need to know the sample mean, which in this case is going to be 0 plus 1 plus 3 plus 4 is 8. 8 divided by 4 is 2. So the sample mean is the same for all of these. It's 2. And then the deviation is X minus X bar. That is the deviation. Oh, it's off the screen, isn't it? Let's do this. Aha. Okay. So 0 minus 2 is minus 2. 1 minus 2 is negative 1. 3 minus 2 is 1. 4 minus 2 is 2. So these are the deviations. Remember, we don't want negative deviations here, so we're going to end up having the squared deviation. Let's make this a little bit bigger. So this is X minus X bar squared. This is now the squared deviation. I said it would come right back, right? So we end up with 4, 1, 1, 4. Okay, so now we have a measure of deviation from some central point, right? It's all measured in positive values like we said we wanted. But at the end of the day, we want one single metric. We want one single number that can represent how spread out all of these points are. So what we do is we are going to let's not put it in the graph. We're going to do this. We are going to take the mean of the squared deviation. Okay. If I were to write that in mathematical notation here, like this is the equation for the mean, it might look something like this. X minus x bar, that's our deviation, right? We square that, that's our squared deviation, and then we're going to take the mean, we're going to take the average, so it's going to look a lot like this equation here as we finish up, right? So how do we do that? Well, we're going to sum up all these values, and we're going to divide by the number of values that we have. That's an average. Sum them all up, divide by the number of things that you have. Take those cups of water, add them all into one, and then redivide them, right? Summing them up is adding them all into one, dividing by n is redividing them, okay? This is the equation for variance. Sometimes also written as the variance of x, because that's the variable we're considering, right? That was what we started with. That was x. Whew. A crazy way of like just saying all that the variance is how far are these points from my mean? Well, some of those distances are going to end up being positive, some are going to end up being negative. So let's make them all have positive units by squaring them. And then we'll just average all those squared deviations. And that will give us one single number, one single metric that we can use to describe how spread out an arbitrary number of data points is. Doesn't matter how many, doesn't matter if I have 4 or 27 or 1,000,000 data points. I can put them into this formula and I will get one single metric that defines how spread out they are. But I needed to ask how spread out are they around the sample mean, x bar? How spread out are they around this imaginary central point within my data set? It's not an actual data point, it's just an imaginary middle point. Okay. So the mean is actually, and this equation is very similar to the variance. It's just that this term here on the top right gets a little bit more complicated. Instead of just being the literal values of x, right, it is the deviation of those literal values, the square deviation of those values from the mean. Okay. Oh boy. Wow, I'm really messing things up. This drawing business is new to me, if you can't tell. I don't want these to look like negative signs. No, I'll just leave that one. Okay. Any questions up to this point about mean and or variance? It's mean of the squared, mean of the sum. Well, it's just mean of the squared deviations. Average of the squared deviations. Okay. Now, the reason why I ask is we talked about how we could also take the absolute value, and that would be a way that we could take these values in the numerator and make them positive. So what if we did this? Instead of squaring them, we took the deviation and then we took the absolute value. And then we did the same thing. We summed them up and divided by n when we were done. Well, we call this the mean absolute deviation. And all that the mean absolute deviation is it is the average deviation from the mean, right? The average deviation from the mean. So it is not the average squared deviation, it's just the average deviation. And in some sense, that's kind of nice because squared values are annoying. And I'd rather just think about it in plain terms. I'd rather just think about these distances literally. Right? These distances here. Right? I don't want to think about squared distances. I just want, it would be nice if they could stay in the same units of the mean, stay in the same units they're already in. Okay. However, in statistics, we don't use the mean absolute deviation very often. Variance is king. That's the crown. Okay. Variance is king when it comes to measures of spread. Okay. And why is that? Why don't we use the mean absolute deviation? It's more intuitive, at least it is to me. It's just the average distance of points from the mean rather than the average squared distance. Okay? Well, let me show you. As a reminder, okay, what does the graph of the absolute value function look like? Well, my x values are my inputs and my y values are my outputs. If I input a 1 and then the absolute value of 1 is 1, the absolute value of 2 is 2, the absolute value of 3 is 3, etc. Right? So the right-hand side of this function is the y equals x line, slope of 1 going up and to the right. Well, the absolute value of -1 is 1. Absolute value of -2 is 2. The absolute value of -3 is 3, etc. So on the left-hand side, whoa, that was really not straight. Yeah. Okay. This is more or less what the function of absolute value looks like. Okay. And as we get into some calculus concepts and doing some optimization, there's a problem with this function. And the problem with this function is right there at x equals 0. Okay. The problem is that this function is not differentiable at that point. And if you're not, if you haven't taken calculus, that just means that the function makes an instant turn, right? Instead of being some smooth shape, well, that's not a function either. Instead of being some smooth shape, right, it jolts or has a disconnect, right? We cannot calculate the slope at that point, at that elbow, at that junction. Okay. Now, why do we care about that? Well, in calculus and in machine learning, I might add, the minimum of a function is a really important thing. Okay. And the minimum of this function is not differentiable. Of the absolute value function is not differentiable. All right, that's bad. We don't like that. So let's think about it this way. If I had a graph, just cleaning up, okay, cleaning up. Okay. In machine learning, we have what we call loss functions. Okay. And a loss function is a curvy, wacky thing. Okay. And at any point where this function, let's actually do that. Stop. All right. At any point where this function's slope is 0, that is a minimum. Right? So wherever this thing turns around from going downwards to going upwards, that is a minimum of the function. Okay? And if we have multiple minimums, we call those local minima. But the one that we're after, the one that we're interested in, is this guy right here. We call that the global minimum. It is the lowest point anywhere on that function. Anywhere on that function. Okay, why do we care about the lowest point on the function? Imagine we had a function that described the quality of predictions that my model was making. And we put it on a graph here. And on the y-axis, we have quality of predictions. I hope you can read this. Man, my handwriting's struggling. Okay. Quality of predictions. Okay? And the lower the value is better. Predictions. And the higher the value is worse predictions. Does that make sense? Well, if I have some function with multiple minimas, like multiple low points here, okay, I would like to pick the x value as a parameter of my model that is going to give me the best predictions possible. Right? I want it to be as low as possible. So this is sometimes called, there's a lot of different names for this, but characterizing the performance of our model with this kind of a function where we want to find the lowest point on the function, and that tells us the best x value, right? This is the king of x values. That's another crown there. That's the point we're really interested in. Okay. This function has a name. It's called a loss function. Sometimes also called an error function or a cost function. Those are all synonyms for each other. You'll hear them phrased differently in different kinds of literature. And this is all that a cost function does is it puts the quality of predictions and plots that against some parameter of our model, some internal weight of our model's performance. And we're trying to find the internal weight of our model that makes the best predictions, right? And that is, we'll call it x star. That's the best parameter that we could possibly find, best weight. Okay. This is a long way of saying that we can make a picture of our model's performance as a graph. And we want to get as low on that graph as possible. That's really what I'm saying. And whatever x value lines up with that lowest point, that is the weight that we want to have inside of our model. Okay? And we haven't really talked about model weights a whole bunch. You could think of like the threshold cutoff in a decision tree as being one of its weights, one of its internal pieces of information that helps it make the best predictions possible. Okay. So if this function is not continuous, if this is an absolute value function, well, I can't solve directly for that point. Because normally I would want to take the derivative, set it equal to 0, then I could solve directly for this point. But I can't do that if my function has this steep change of directions in it, this point where it's not differentiable. Okay, so this is a really long-winded way of saying, in statistics, the mean absolute deviation, it makes more sense than the mean squared deviation. It would be really nice if we could use mean absolute deviation to talk about how spread out our data points are, but it's going to cause us a whole bunch of other issues down the line if we use the mean absolute deviation rather than the mean squared deviation. But we're still going to come back. We're going to talk about the mean absolute deviation a little bit more, even so. Okay. What if I have my variance function, xi minus x bar squared. There's my squared deviation, and I'm averaging it, right? This here is an average. This here is the squared deviation. Probably overemphasize that, okay? What if I took the square root of this whole puppy? Would it cancel out with this squared term here cancel out with the squared root? No, it wouldn't. Unfortunately, it doesn't work quite that nicely. Okay, it would be cool if that's how the laws of square roots worked, but that's not how it works, unfortunately. So if I take the square root of the variance, I do not get the mean absolute deviation. It would be nice if I did. It would be nice if this gave me that, but it doesn't. It gives me something actually pretty close to the mean absolute deviation, but not exactly the mean absolute deviation. They're numerically, they're going to end up being in the same ballpark as each other, but they're not quite the same. When I take the square root of the variance, I get something called the standard deviation. And the standard deviation is defined as being the square root of the variance of whatever variable it is we're considering, the variable we've been calling x. That is the definition of the standard deviation. Now, what's nice about the standard deviation is even though it doesn't get us back to mean absolute deviation, this kind of way of thinking about spread out numbers that is rather intuitive, it does, however, put the measure of spread back in the same units as the mean, right? So if I have a bunch of people that are making money, and somebody's making 90K, and somebody's making 100K, and someone's making 120K, and 130K, right? And that's all in dollars, right? That's my unit. If I calculate the variance, the units of the variance is going to be squared dollars, which doesn't make a lot of sense. But once I square root it, I end up with the standard deviation being represented in dollars. So the sample standard deviation we represent with the letter S. The population standard deviation we typically represent with the Greek letter sigma. Okay, so this is population. Oh, I've got that backwards, excuse me. This is the sample standard deviation, and this is the population symbol for the standard deviation, right? But the standard deviation always ends up in the same units as the mean. So the standard deviation will be in dollars, whereas the variance would not. So standard deviation, being the square root of the variance, is able to recover some of the intuitive nature of the mean absolute deviation, but not being mathematically exactly quite the same thing. In fact, I've told some of my students in the past something that would make statistics professors freak out. And I tell them, think about the standard deviation as if it was the mean absolute deviation. Oh, wow. Pedantic people will not like that recommendation. Okay. Think about the standard deviation as if it was the average distance of points from the mean. That's not what it is, but it's in the ballpark. If you think about it that way, you're not going to be very far off in how you approach it. Okay. So to recant what I just said, the standard deviation is described or defined specifically as being the square root of the variance, which is not the same thing as the average distance from the mean. That's what that's what the mean absolute deviation is. It's the average distance of points from the mean. But it is in the ballpark. In the ballpark. Okay? All right. This iPad drawing is a little bit of a mess now. I'm going to switch back to our notebook, and we may come back to this a little bit later, because I want to just kind of summarize my ramblings here, a lot of different points that I've made with a little bit of code. Let's see if I can switch back and not mess this up too much. Aha, okay. I think we're back. Okay. Bum, 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 bum. Right, what have we learned? The mean, we sum all the values, divide by the number of values. We put everything in one jug of water, then redivide it up into cups. It's affected by outliers. It's seen as like the center point of all of the data points, sometimes called the center of mass. Right? It is the most widely recognized statistic. We talk about averages all the time in society. It's used to represent what's typical for a variable. And although it is a useful summary statistic, some information is lost when we use what we call an aggregate measure. Right? I've taken 4 or 100 or 1,000,000 data points, and I'm summarizing something about those data points with one number. And whenever I do that, it's a little bit dangerous. Right? I'm losing some amount of information that was originally present across the whole data set because I'm reducing that down to just one single metric. Okay? And you can kind of see that in this joke. Whenever Bill Gates walks into a bar, everyone present becomes a millionaire, on average. Right? It's not really very useful, but Bill Gates is this huge outlier, right? It means they're susceptible to outliers. And so it's describing the average net worth of people in a bar where Bill Gates is. It's not really a good use of the mean, right? So it's not a perfect measure, and we lose a lot of context when we calculate the mean, particularly if we lose context about the presence of outliers, then that's when we can be in trouble. Okay. We talked about how x sub I in our mathematical notation represented each different element in our list element-wise. And that helped us see that the variance was the average squared deviation from that imaginary middle point we call the sample mean. Okay. So I'm going to do something for you here. A little test of intuition. I'm going to generate 2 random distributions of data points. Okay. But the range of one ranges between 25 and 75. Okay. So what's the range here? The min minus the max, or the max minus the min, it's 50. Whereas the range here is 100, right? So the variable variance 2 or V2 is twice as spread out as variance 1. Okay? Variance 2 is twice as spread out as variance 1. If I graph them, looks like this, right? Roughly, second plot is roughly twice as spread out as the first plot, on average. Okay, but here's my question. How much bigger will the variance of plot 2 be compared to plot 1? Variance is a measure of spread, a measure of dispersion, a measure of these squared deviations. And if one variable is twice as spread out, how much bigger will its variance be? Let's calculate it. Okay. So we're going to grab our variance df and grab v1, calculate its variance with pandas, about 216. And if we do the same thing here with variance v2, it's about 878. How many times bigger is variance 2 than variance 1? Roughly. Well, it's about 4 times bigger. Even though plot 2 is only wider by a factor of 2, its variance is bigger by a factor of 4. By a factor of 4. And why is that? It's because of that squared deviation, right? In fact, I can get this to be even closer to an exact 4-to-1 ratio if I make my sample size here huge. It's going to make the graphs look silly because they're just going to be like solid blue lines because of all the overlapping points. There's 10,000 dots being graphed in both of these. And now the variances should be pretty darn close to 4-to-1. Again, variance, that squared nature to it is really inherent in its essence, right? So I cannot compare variance values and go, oh, looks like V2 is 4 times wider than V1. That would be an incorrect assessment. I have to do what? Well, if I were to take the square root of these numbers, I get the standard deviation, then we would be back in terms of the units of the mean, and the standard deviations would be comparable. The standard deviation of plot 2 is twice the standard deviation of plot 1. But the variance is 4 times bigger. Okay? So the standard deviation is like a regularized, normalized, standardized, whatever you want to call it, version of the variance put back in the units of the mean, and standard deviation values can be directly compared, but variance values cannot be directly compared, at least not in a way that will lead us to the correct assessment, so to speak. Okay. So we've talked about the variance. I'm gonna copy and paste some things for time's sake. Right? Here's our fake little variable x, right? And a couple of different ways we can get the variance. If we use NumPy, we have to pass this extra parameter called denominator degrees of freedom, because NumPy by default calculates population parameters, but Pandas by default calculates sample statistics. Right? So if I'm doing this sample variance, I actually divide by n minus 1 in the denominator. I think in my iPad graph, I just put it over n. But if I want the sample variance, I'll divide by n minus 1. If I want the population variance, I'll divide by n. With big sample sizes, it ends up being a negligible difference. And we'll talk a little bit on another day about why n minus 1. I don't think we're going to have time to delve into that today. We're already a bit over time. Standard deviation is the square root of the variance. Okay? So what if I take the standard deviation of V1 and V2? Well, V2's standard deviation should be about twice that of V1, because it's twice as spread out. So you can compare standard deviation values and get the right assessment, but not variance values. Okay, this is what we've been getting at. We've been really spending a lot of time on variance and standard deviation so we could have a good grasp on something called covariance and correlation. Okay? And we're moving from the world where we just look at one single x variable at a time to now we're going to look at a pair of x variables, and we're going to ask, how do they relate to each other? Two different variables, what's their relationship to each other? So we're making the leap from univariate exploratory data analysis to bivariate exploratory data analysis, and we're gonna try and wrap our heads around covariance and correlation, and then we'll call it a night. Okay. All right. So here's the equation for variance on the right. We see the squared deviation here, right? I could break up that square and write the terms separately and have the first deviation multiplied by the second deviation, right? This is equivalent to this. Writing the squared term is the same as writing them multiplied side by side, right? Okay. The only difference from the variance equation to the covariance equation is that we change the second set of terms from x to y, to some other variable, right? So we're going to say we have two variables. We have variable x, we have variable y. And we're going to ask, we're going to multiply their deviations against each other, right? So the covariance is the average product of the deviations of each pair of data points from their respective means. So we have the sample mean of y, and we have the sample mean of x bar and y bar. Okay? But the equation and the calculation and the intuition around it is all highly, highly related. Okay? And in fact, if I took the covariance not of x and y, but of x and x, right? So I had xi minus x bar, xi minus x bar, well, I would have the variance. The covariance of any variable compared to itself is just the variance. It's a lot. I know I'm dropping a lot of information on you, but I just hope you to see that once you understand that this parentheses expression is just a deviation from the mean, and then the sum and divide by n is just an average, then this crazy notation becomes a lot more digestible. And I hope I'm emphasizing enough for it to sink in a little bit. Okay, let's learn some intuition about the covariance. What is the covariance? Well, it's a measure of how two variables co-vary. How does one variable change as the other variable changes? Does it go up or down, right? As x goes up, what happens to y? Does y go up on average, or does y go down on average, or does y stay the same or do nothing, right? How does one variable move as the other variable moves, okay? So I've got two pairs of variables here in two different data frames. We've got data frame A and data frame B. And I want you to look at these numbers, and I want you to see that in data frame B, I have exactly the same numbers. Everything's just multiplied by 10. Okay? So the patterns in the data in these two data frames are exactly the same, but the scale of the numbers is different by a factor of 10. Same data points, just spread out. Okay? And we'll see that as I graph it here. Okay? So the left side is the variables in data frame A, and the right side is the variables in data frame B. Okay? All right. Here are my questions. Where are my questions? Here they are. Which of the following graphs shows a stronger linear relationship between the two variables? A stronger linear relationship. And as you think about it, this is a trick question. The strength of the linear relationship is identical between these two. All these points are exactly on the same line. It's actually a perfect linear relationship. Okay? So the scale of the numbers, the range of the numbers, does not say anything about the strength of the linear relationship. These two have exactly perfectly linear relationships between x and y across these two graphs. Okay. Now that I've told you that, which of these two graphs do you think has the greater covariance values? Singular value. It's one metric. Well, if covariance means we multiply deviations from the mean, the deviations from the mean in the right-hand graph, if the mean's like here, some center point where my cursor is, these deviations are a lot bigger than these deviations. If I'm multiplying the deviations between x and y together, I'm going to end up with a big covariance value for this guy on the right and a small covariance value for this guy on the left. In fact, the covariance of the graph on the right is going to be about 100 times bigger than the graph on the left. And why is that? Well, because my data was off by a factor of 10. And because I'm multiplying them together, 10 multiplied by 10 is 100, right? So the covariance of this right graph is 10 times bigger than the covariance of the left graph. And what we're actually seeing here is something very similar to what we saw with the variance, where the variance values, if you compared the raw numbers, didn't tell you about the spread of the data, didn't help you compare the spread of the data. Same thing with covariance. The raw covariance values don't tell you anything about the strength of the linear relationships, and the raw covariance values don't tell you anything about well, they could tell you generally about which one is more spread out, but they don't tell you about the strength of the linear relationships. I've got that summarized down here, right? Variables that have a different scale or range will have different covariance values irrespective of the strength of the linear relationships between x and y. The more extreme the units, the more they deviate from the sample mean, the more extreme or further away from 0 the covariance will be. Covariance does not tell us anything about the strength of the linear relationships between two variables. And then I recant. A slight caveat, a covariance of 0 would tell us that there's no linear relationship, but a non-zero covariance doesn't tell us anything about the strength of the linear relationships. Okay, let's think about this a little bit more. And let's look at this image, make it bigger. Okay, here's a graph on the top. As my x values increase, on average, are my y values getting bigger or getting smaller? Well, as my x values increase, my y values are getting smaller. So this is a negative covariance. And you can see that because the points kind of have a negative slope. If I was to fit a line of best fit to this, hey, that's what linear regression does, which we're going to get to. Okay, it's building up to that. This top graph has a negative covariance. As x increases, y decreases. The graph on the bottom has a positive covariance. As x increases, y also increases. What about the covariance of this middle graph? As x increases, y exists. The covariance of circular-ish blob is pretty much 0. Pretty close to 0. Right? So same with this graph here. As x increases, what is y doing? Y is not really going up or down. There's no up or down trend to the position along the y-axis as x increases. Right? So this is a covariance that's close to 0. And in fact, really the only useful thing about covariance is we look at the sign. Is it a positive or negative covariance or 0? And then the number, it doesn't matter if the number is 500 or 5,000 or 5 million. It doesn't really tell us a whole lot. It just tells us that the data we were working with used big numbers. The bigger numbers the data we started with uses, the bigger the covariance is going to be. And again, covariance values are not directly comparable. The sign of the covariance is really useful, positive or negative. Or if the covariance is 0, that's informative. But everything else is kind of a wash. Okay? In reality, covariance is kind of used as an intermediate calculation in a lot of other really important, really interesting processes. We don't usually look at the covariance directly and go, aha, it's positive, because reasons we'll talk about in a second. Okay? So the reason why I've spent so much time on the covariance is because if you understand covariance, okay, you will really understand correlation. Correlation is going to be a cinch if you understand covariance. All right. Couple other trick questions. Okay, so which of these following graphs has the greater covariance? Right? They have positive slopes. They both have positive covariance. But this right-hand graph is more spread out along the x-axis. Remember, we're multiplying the spread outness on the x-axis, the deviations of x, multiplied by the deviations of y. So our right-hand guy here is going to have a larger covariance. But they're both positive covariances. And the fact that one covariance is larger than the other, it doesn't really matter to me, actually. But just trying to build our intuition. Let's actually print out some of these covariances so I can prove to you that I'm not making it up. So A and B, those are our two data frames. Make sure I run this. Okay. Second covariance is about 100 times bigger than the first one because the data points are 10 times more spread out across both dimensions. 10 times 10 is 100. In this instance, only one of them is more spread out by a factor of 10. So let me copy paste again. So this time we should see that one covariance of one is only 10 times bigger than the other. There you go, about a factor of 10 difference. Okay. Which of these has a greater covariance? The patterns in the data are the same. The data are perfectly linear in their relationship. Remember, the covariance doesn't actually tell us anything about the strength of the linear relationship. Well, these are going to have covariances that are equally as extreme, equally as far away from 0, but they're both going to be with different signs, right? Positive covariance for B, negative covariance for A. And that sign is what we're really after. Is it negative, positive, or 0? Okay. And I just reiterated that in writing here. Covariance only measures the direction of the relationship, not the strength. It is not useful to directly compare covariance values, since the value itself will change based on how spread out the variables are. So covariance values are unbounded. They could be anything from infinity to negative infinity. Okay. All right. Move on to correlation, and we'll wrap up. What is it about the covariance values that makes it so that only the sign of the metric is useful? Well, it's because the covariance changes so wildly based on the scale or the range of the data. So if only we had some way to measure how spread out data was so that we could control for that scale or that range of data, right? Well, that's literally all that the correlation coefficient is. The correlation coefficient, lowercase r, is the letter that gets used for it in statistics, is the covariance of x and y divided by the product of the two standard deviations of x and y. What is standard deviation? It's a measure of how spread out our data points are, right? So we are undoing the very thing that makes this number 100 times bigger than this number, because the standard deviations here on the right are going to be 10 times bigger than the standard deviations here on the left. And if I multiply those standard deviations that are 10 times bigger than one another together in the denominator, well, that's my factor of 100. So just like standard deviation normalized variance, put it back into sensible terms, put it back into the units of the mean, and took it from this weird squared thing and gave us numbers that we could work with and make sense of, and was more intuitive. The correlation is an improved version of the covariance. We call it a standardized, or sometimes some people call it a normalized version of the covariance. But all that it is we divide by the product of the two standard deviations, standard deviation of x, standard deviation of y. And what this does is it makes it so that the correlation can no longer go from infinity to negative infinity. We've taken out all the spread of the data, and now correlation ranges between -1 and +1. Correlation cannot be outside of those bounds. Okay. And correlation now will measure both the strength and the direction of any existing linear relationships between two variables. Okay. Covariance didn't say anything about the strength of linear relationships, but correlation does because of that standardization, because we've factored out the spread of the data. Okay, so a correlation of 1 indicates a perfectly linear positive relationship. A correlation of 0 indicates there's no linear relationship, and that changes in one variable do not predict the changes in another. And a correlation of -1 is also a perfect linear relationship, but with a negative slope. If it even has the slightest bit of negative slope, the sign will be negative, right? So the sign here just tells you positive or negative slope, and then this range between -1 and 1 tells you the strength of the linear relationship. Back to our graphs. Which of the following two graphs has a higher correlation? In other words, which of the two graphs has a stronger linear relationship? You might remember I already asked this question. Well, both graphs have an identically strong linear relationship. They're perfectly linear, right? And both have positive slopes. So both of these should have a correlation of 1, or very, very close to 1 with some Python rounding errors. Let's see. Make sure I've run this code cell so that my Here's the standard deviations of x and y. Here's the standard deviations of, in the second graph, right? Both are 10 times bigger. Multiplied together, they're different by a factor of 100. And here's my covariance. Covariance divided by the product of the two standard deviations gives us 1. Or I can use the simplified function that already comes inside of pandas. The correlation is 1. And I can do the same thing for data frame B if I want. It's going to give me the same numbers, but for whatever reason, it gives me a tiny rounding error this time, which is we're going to ignore and pretend that they're all exactly 1. Okay. Standard deviation improves variance, puts it back in human understandable numbers. Correlation does the same thing to covariance as we factor out the spread of the data and make that a non-factor. Make it so they don't differ in that way. Okay? But I really want to stress that correlation only measures the strength of linear relationships between variables. Okay? So if we plot a scatter plot of x and y and the numbers are exactly on a line, well, that's going to have a really extreme correlation, if correlation equal to 1. Okay. And the more this is kind of like a cigar-shaped cloud of points, the correlation drops a little bit. And as it becomes more circular, less linear, correlation drops a little bit. And a circular cloud of points has no linear trend, right? So its correlation is 0. And as the slope becomes negative, we get the same values, but with a negative sign in the front. Right? So the slope, positive or negative, tells us if the sign should be positive or negative. And then everything else about correlation is the strength of the linear relationship. Okay? So positive slope, positive slope, positive slope, nothing. Negative slope, negative slope, negative slope. By the way, this middle guy, what is the correlation here? Well, how much does y vary by here? What is the deviation in y? What is the standard deviation of y, I should say? Standard deviation is 0. Right? There is no change in y. There is no spread. This is exactly the same as our single data point example, but if you only looked at it along the y-axis, right? So here in the middle, there's no number for this middle graph because the standard deviation here is actually undefined. Undefined. If the standard deviation of y is 0, and then I get a divide by 0 error, and the whole value becomes undefined. So you can't calculate correlation if you don't have at least a little bit of deviation, a little bit of dispersion in both of the variables. At least a little bit. Okay. Now here's something a little bit crazy. This last row, this is an example of data that has patterns to it, but the patterns to this data are non-linear. Okay. And the correlation of all of these is 0. Okay. And this harkens back to what I said before, that anytime we take a whole bunch of data points and try and summarize them with one aggregate measure, summarize them with a single number, we're going to lose some context. We're going to lose some nuance. We're going to lose some information. Okay? And in this sense, correlation is a really useful metric, but it only looks at linear relationships. It says nothing about nonlinear relationships. So there could be really distinct patterns to our data that do not get picked up by measures of correlation. Okay? It only finds linear relationships, doesn't do anything with nonlinear relationships. And as a way too early of a sneak peek, part of the reason that neural networks are so awesome is that neural networks can fit non-linearities in data. They're not limited to linear relationships. In fact, neural networks exist to fit to nonlinear shapes, and in fact, they're way too good at it. They fit to noise really easily, and neural networks will overfit and fit to patterns in the data that aren't really even there. because they get so good at fitting nonlinearities. And that's a big part of why neural networks are such a powerful category of machine learning models. Okay. So correlation. It's the covariance divided by the product of the standard deviations. It tells us the strength of linear relationships. And this next graphic here is something called Anscombe's quartet. And it's just to reiterate the point about how summary statistics are a summary, right? As we aggregate into those single numbered measures, we lose some information. And if you look at these 4 graphs, they all have exactly the same mean, median, variance, standard deviation, covariance, and correlation. Identical among all 4 of those graphs. The patterns to the data are very different, but the summary statistics across all 4 of them are identical. Okay? So we have to be, summary statistics are very useful. This exploratory data analysis is very useful, but it doesn't tell us everything. It's still really important that we look at our data visually and let our pattern recognition brains be able to go, ah, that one's curved. Ah, that one's kind of linear with an outlier. And that one's a cloud of points, so that one's not going to have a perfect correlation. You know, like there's things our brains can see in an instant that our summary statistics might not fully grasp, right? My brain immediately sees, oh, there's patterns in this data. This bottom row, correlation is totally blind to those patterns, but my brain's not. So we'll talk more about the variance and covariance matrices next time. But basically, whenever you have a data frame, you can easily calculate the variances and covariances across the whole data set with one single function call. And you can easily calculate the correlations across the whole data set with one single function call. Okay? We'll talk more about this next time. I want to show you that, you know, getting back to our housing data, right? If I load my housing data and I grab the numeric data types only, okay, here's my correlation matrix. There's a lot of numbers in here. The main diagonal is always 1 because every variable is perfectly correlated with itself. And if I look through here, I want to find really extreme values, correlation values that are close to 1 or close to -1. If it's around 0, I'm not so interested in it. And in fact, more than anything, I'm interested in how my x variables correlate with my y variable. So this particular row is of a lot of interest to me because this is the year sold row. And if there's something that has an extreme correlation here, that means, oh, that x variable has a strong linear relationship with the price of the home, and it may be a strong predictor of my y variable. It may help my model do a good job. And we'll dive into this more next time. I'm gonna paste in the code here so you can see what we're going to talk about, but we can generate a correlation heat map. And we're really interested in dark blues and dark reds. The grays we don't care about, right? And we particularly care about the sale price row or the sale price column. You can look at it the same. It's a mirror image reflected across this red main diagonal. Okay? So overall quality is very positively related to price. Kitchen above ground is negatively related to price. The great room living area is positively correlated with price. Having an enclosed porch is negatively correlated with price. Right? And so you can kind of see the strong variables, the strong correlations, those are going to be our most useful and most valuable variables across our housing data set. They're going to be the strongest predictors of housing price because they have those strong linear relationships, and linear regression is linear regression. It's fitting lines to things. We can also use something called the Seaborn pair plot to give our brains a chance to look and see, are there some nonlinear relationships in this data that maybe correlation is missing, but that my brain could catch? And it's going to take it a minute for this graphic to generate. But I'll tell you as it's generating, yes, there are some nonlinear relationships here. Yeah, they're a little bit tricky even to catch with this set of graphs. But if you see any like little bit of curvature to some of these data points, like a little bit of curvature here, a little bit of curvature here, that might be telling that, hey, maybe only using linear relationships here to determine how to predict y, to model the relationships between x and y variables, maybe that's not going to be sufficient. Maybe we also need some nonlinear ways of capturing these relationships as well. All right, we've gone way over time. Thank you if you're still here. And if you had to jump in and out and you maybe have to catch the recording, that's awesome too. That's why we record. Okay. And we're going to continue this discussion next week. And let me tell you, next week we're actually going to fit a linear regression model. We're actually going to do some real machine learning. We're not going to be stuck in exploratory data analysis land forever. Okay. But our discussion, particularly of correlation, is going to become very, very important to what we do next week. And we will revisit these last few code cells and talk about them in greater depth next week. Okay. Even if you coming into today felt like you had a good grasp of mean, median, variance, standard deviation, covariance, and correlation, I hope you understand them a little bit better today. Maybe your brain has made some connections it hadn't quite made before, and I hope it's been of benefit to you. Please reach out to me on Discord if you have any feedback about the code challenges, or you can find me on LinkedIn or Twitter or any of the ways you can get a hold of me. I'm really curious what you guys think of those. Please go to the temsy.com/code challenges and give those a try. And I'd really love to hear what you think. If you think that's a useful thing, if I should put more time into making more of these and cooler, more advanced ones, stuff like that. Or if it's just, you can find code challenges anywhere. So that's an email. I don't know why I'm showing that. Okay. Thanks, everyone. Have a great evening. I'll let you go. And can't wait to hear from you about code challenges, and see you at next week, same time, same place, at the very latest, if I don't see you before then. Thanks, everyone.